we know it's not the alkalinity of the machine that's causing any of the results that people are having. And so then we come to the surface tension, the microclustering, all these other words that people use to talk about how the water is absorbed in your body. So H2O absorbed in your body, going through an ionizer machine, how is it affecting? Is it microclustering? And this T-test that a lot of the people out there are doing, is that showing the actual absorption?
Yeah, you know, it's a great question because for a long time, the researchers found that this water had therapeutic effects. And that raised the question, how, why, what's the mechanism? And there became these ideas of flickering clusters, microclusters, different structures, all these different concepts to maybe explain it. And it was investigated, and unfortunately, or fortunately, it was found that wasn't the answer. All right, I know there's been even data using like a nuclear magnetic resonance spectroscopy, which will show the different resonance frequencies of the bandwidth, and like look at the difference. It turns out that has more to do with the pH, deviations from neutral pH and other issues, and nothing to do with water cluster size. So it's simply not a valid test. And that goes also to your point with like making of the tea. It is a pretty cool demonstration, I admit. You take, you know, typically has to be like a green tea, and you put it in, and there's normal water, you don't really see much of a color change, but you put it in the high pH alkaline water, and it's, you know, very green. Then the claim, of course, is that maybe the smaller water clusters or something can, you know, bring out the tea molecules. Unfortunately, yeah, that's not true. Actually, fortunately, that's not true. Maybe we'll talk a little bit about some potential side effects if that phenomena were actually occurring in our body. It could be very disastrous. But so what's happening? How do you explain the making of the tea? And it's actually quite simple. It turns out that the pH and the green tea acts as a pH indicator. Okay, so this is something that, you know, elementary children do for their elementary school experiments with like cabbage or different types of foods. You can put it in vinegar, and then you put it in your tap water, you put it in baking soda, and it changes different pHs. And turns out green tea works like that also. It's just it works like a pH indicator. And so people can certainly try this at their home. They could take a green tea and put it in, you know, let's say, you know, bottled water or something, let it soak for a while, and then add a little bit of baking soda, and it'll start to turn green, right? Or take the tea and put it in their high pH alkaline water. It's nice and green, and then add a little bit of acid to it, and that color seems to disappear. Okay, now I have to say that there might be a small amount of extra tea molecules in the tea using alkaline water, because tea has various phytochemicals, phytic acids and things that, the higher the pH, ionizes some of the molecules, and that can help to extract some of those things out. It can also prevent others from coming out. Okay, so there can actually be material differences on that level, but in terms of it being therapeutically or clinically different or something, it's not really there. It's just, you know, marginal changes. It's generally just a pH issue. Okay, so it's not about the microclusters or changes in water structure or anything like this. And that, like I said, has been specifically investigated. In fact, I've done this myself, looking at doing some specific studies using spectroscopy studies and measuring even the surface tension of the water, just to see if there was anything. And in fact, the surface tension seems to, if anything, increase with the higher the pH. And that has to do with hydroxide ions, which are responsible for the high pH being at the surface of the water. But anyway, again, it's not the structure of the water. The water structure does not change at all. Water is, it's very important that it has the structure it does have, because our bodies, over the billions of years since we've been using water, so to speak, since the beginning, the earliest stages of life, use special protein carriers called aquaporins, and water enters the aquaporin in a single file, linear and separated fashion. Okay, so it can't go into aquaporin altogether. In fact, the reason why aquaporins were even hypothesized to or theorized to exist is because water can't easily cross the cell membrane into the cell very easily, because the cell membrane has a layer of fat around it. It's called the lipid bilayer. And so water, which is a polar molecule, it's not able to penetrate the cell membrane very easily at all. Okay, it has to, and so when they do the studies, you can all of a sudden see that the water goes from one side to the other, much faster than it would be predicted by the permeability of water through the cell membrane, and so-called Brownian motion. So it's like, how is this happening then? Well, there must be certain protein channels that are allowing the water to permeate from one side to the other, and indeed that was found. These protein channels called aquaporins, and there's different aquaporins, like aquaporin 1 through 4. Some of these are found in the kidney, others are found in different areas of the body, and so on. But they have similar structures, slight differences. But the fact is, the water with 104.5 or 4.5 degree bond angle specifically is what allows it to associate with specific charges in the channel itself to allow it to enter into the cell perfectly, again, in a linear, separated fashion at very fast rates. So if microclustering were a thing, or changing the structure or the hydrogen bond angle, you would literally prevent the water from entering into the cells, right? And there's a whole sorts of problems that would be associated, metabolic consequences that would be caused with this, and that goes even with and other claims, that this is going to increase your cellular hydration to so much more. That could also be problematic. One of the hallmark signatures of cancer, for example, it's in the initiation and metastasis progression of the disease is actually a disordered structure of the water inside the cells itself, and increases in cellular hydration, because that induces a proliferative signal to start the spread of the cancer. So it's fortunate that we can't simply change the water structure in any of these ways I've talked about. Otherwise, the consequences would be disastrous and fatal.